All right, so 我 quickly 打了一下 here. So for the homework, let me quickly talk about some common stuff. First of all, page 2. On figure 1.1, draw a vector diagram that determines the magnitude of the resultant of two forces. Most of you have problems with that question. Let's look that one. So here. Right, so it's asking you to draw vector diagram. So you need to draw something. Did you draw something? So first of all, we have 8 and 6. Did you say which one is which? No, so you can pick 8 here and 6 not here, but along this direction because it's already giving you this angle is. So 6, 8, and then use the parallelogram, we draw the diagonal, then you can calculate how large it is, right? So a lot of you missing this diagram. And a lot of you draw the parallelogram, I don't even know what that shape is. Somebody draw it like that. What's that? Is that a parallelogram? You? Okay. Okay, so you draw a parallelogram, so make sure it's a parallelogram, okay? At least this here should be parallel with this one. This here should be parallel with this one. Okay, that's the first question. Second one, that's mostly common that you got wrong, is the last question, which is on page 4, I think. Yeah. The last one here, most of you got it wrong. A lot of you just directly say the gradient is the acceleration. Well, it is related to acceleration. Let's look at the graph. This graph is a distance t squared graph. In Suvat equation, how can we calculate s? S equal to, when initial velocity is 0, it should be, right? Did it say that it starts from s? Yeah. Okay, so which means ut plus 1/2 at squared. This term is 0. It's supposed to be. There is a systematic error because it's supposed to pass through the origin, but it didn't. So what the function is, it's actually s equal to 1/2 at squared. Now, this is your y-axis. This t squared is your x-axis. What exactly is your gradient? 1/2a. So how can you calculate acceleration? Gradient times 2 equal to acceleration. Most of you forgot to times 2. Okay? All right, so that's the major issues from your homework. Major issues from your homework. Okay, so that's it. Today we're gonna look at A1, kinematics. So, okay, so A1, in this chapter, what we're gonna do is, we're going to look at, first of all, motion of the body through space and time can be described and analyzed in terms of position, velocity, and acceleration, which you guys have already learned it in MIP. So we're just quickly run through them. Velocity is the rate of change of position or displacement. And acceleration is rate of change of velocity. Okay? All of them, displacement, velocity, and acceleration are vector, which means they have direction. Okay? The change in position is what we call displacement. And the difference between distance and displacement, what's the difference between distance and displacement, Jessica?
Distance is like you pass through, but then displacement is like here and here.
Where and where?
This and this. distance is like you walk a circle, and then your distance is the length of the circle.
Okay.
And then if you walk a circle and then come back, your displacement is.
Okay, well that's correct. That's true. Okay, she gives us an example of distance and the displacement. Okay, so the fundamental difference between distance and displacement is one is scalar, the other is vector. Which one is scalar? Distance, which means it only has magnitude. It doesn't have direction. But displacement is a vector, so it has direction. And it's always pointing from the starting position towards the ending position. So if you run a circle where your starting position and your ending position is overlapping, then there's no straight line between the starting position and the ending position, so that the displacement is 0, right? Okay. And the Somebody equation we already learned about, so everything we have learned in MYP, we're just going to quickly skip. We will do some review, but it's just a recalling stuff. So our A1 will be pretty fast. Motion with uniform and non-uniform acceleration, that's something new that we didn't learn in MYP, so we're going to spend more time on this. The behavior of projectile in the absence of fluid resistance, and the application of the equation of the motion result in the vertical and horizontal components. This is also something new that we're going to spend time with. And the qualitative effect of fluid resistance on projectiles, including time of flight, trajectory, velocity, acceleration, range, and terminal speed. Okay, so those are the things that we're going to focus on today. So, as we have already talked through the distance and displacement, quick compare. We're going to skip this part, but it's a good thing to know what is those 3 words, right? So first of all, mechanics. What is mechanics? Mechanics is the branch of physics which concerns itself with forces and how they affect a body's motion. In Chinese, which we translate mechanics as 力学. Kinematics is the sub-branch of a mechanics which studies only a body's motion without regard to causes, which translate to Chinese is 运动学. So it's related to the motion, right? Without concerning its causes. And dynamics is the sub-branch of mechanics which studies the forces which causes the body of the motion, which translate to Chinese is 动力学. So we're gonna discuss about the forces. The main focus is the forces, right? So that's the thing. So if you can draw a tree diagram or whatever diagram to represent the relationship between those 3 words, how would you draw it, Nana?
Mechanics is the main branch.
Okay.
And then kinematics and dynamics are the sub-branches.
So maybe like this. This is our mechanics. And under each one we have kinematics and dynamics. Like that, right? Okay. So, very good. Alright. So we have those 2 famous scientists, with Galileo mostly focused on the developing theories and hypotheses in kinematics, and Newton's focusing on dynamics. Okay. Right. The 2 pillars of the mechanics. Alright, so in kinematics we discuss about displacement, velocity, and acceleration, which is the same, the key core part of SUVAT, right? The 5 letters. Do you still remember what those 5 letters represent? Ashley, S is? SUVAT, S is? V 是什么? Okay. Yeah, which velocity? Okay, I'll spare you this time. Jason, S is displacement. Jaslyn, U is initial velocity. Ashley, V is 你说你知道 V 的
initial velocity 后面的 velocity
那叫什么 velocity 呢
Okay,
Final velocity, exactly. Alice, what's A?
Acceleration.
Acceleration. And T is? Everybody? Time. Okay. Alright, so now, first of all, we start with changing position. What's changing position? Displacement, right? Displacement in English literally means to displace something, right? You move something from here to here. That's what we call displace, right? To change something's position. So, oops. Alright, so let's see. So this is Freddie, our friend. Well, you don't want to be friends with Freddie because it's a fly. Oops. But yeah, Freddie, his request is food. So what Freddie is gonna do is to fly to his food, right? So in this process, Freddie moves himself or moves itself, right? To displace itself to go to his food. Okay? So we say, what is this 6 meter? It's the displacement of, well, you don't want to say your friend, so let's just say Freddie, right? Freddie's displacement is 6 meter. But hold on. We say that displacement is a vector, which means other than magnitude, they also have direction. So what other information should we have in order to say it's actually a displacement? To the right. 6 meter to the right. That's the displacement information of Freddie. So the distance Freddie travels is simply just how far he has flown, which is 6 meter, without regard to direction, right? Okay. So distance is simply just how far something has traveled. It doesn't necessarily to be a straight line. So if Freddie decides to take a route of it, which let's say this is 10 meter, the length of this path is 10 meter, then the distance that Freddie has traveled is 10 meter, but the displacement is still 6 meter to the right, right? Okay, very good. So 6 meter in the positive x direction or to the right, Sometimes if we set a coordinates, we can just use plus, minus to represent the positive direction, negative direction, corresponding to the direction of the axis. So let's say in this case, it's positive x direction, so plus 6. X equal to plus 6 meters. Okay. Any questions for me? Should be easy. Alright, let's move. So this is displacement A, and this is displacement B. Then the total displacement should be the vector sum of A plus B. Let's say A here is, no. Let's say A here is, let's just assume that one block is 1 meter. So 1, 2, 3, 4, 5, 6, 7. Actually, this is 1 meter. It will be faster. 1, 2, 3, 4, 5, 6, 7, 7.5 meter. And here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 meter. So what is the total displacement? 他已经说了，那就 ignore it. What is the total displacement after this? (2.5 meter to the left or negative 2.5 meter? right? Negative 2.5 meters. Very good. Okay, so that's what it means for displacement. Remember, distance is scalar, so if we are asking the total distance, then that should be 17.5, right? Or in this case, just 15 plus 20, 35 meter is the total distance. But total displacement is negative 5. Negative 5. Okay. Okay, let's move. We know that the displacement is just two position. Final position minus your initial position, right? Displacement is final position minus your initial position. Okay, let's move. Too easy. Skip. Skip, skip, skip. Speed and velocity. Alex, what's the difference between speed and velocity?
Speed is scalar and velocity is vector.
Okay, speed is scalar, velocity is vector. So, in short, we can say that velocity is speed with direction, right? Okay. So, velocity is a measure of how fast an object moves through a displacement. So, velocity is also a vector, and it's defined as the rate of change of displacement. Easy, easy, go, go, go. Speed, on the other hand, is the rate of change of distance. Distance is also scalar, so the rate of change of a scalar is also a scalar. How do we calculate average speed? Total distance divided total time. How do we calculate average velocity? Total displacement over total time. Okay, very good. Question. So let's say our field has a circumference of 400 meters. Let's see. How long did it take for you to run a lap? Roughly, just an estimate.
3 minutes.
Okay, 3 minutes. So that's about 180 seconds, right? What is Vinci's average speed? We should use 400 over 180 to calculate, right? What about Vinci's average velocity in completing one lap? 0, because total displacement is 0. So Vinci's velocity is 0. PE teacher might say, what's happening? But in physics, that's true. Vinci's velocity is 0. But we're talking about Vinci's speed, then it's 400 divided by 180. 180, okay? Alright, let's move on. Acceleration is the rate of change of velocity. So as long as there's acceleration, velocity should change. Not necessarily just magnitude. Sometimes magnitude don't change or just stays the same, but it changes the direction of the velocity, right? Okay. So where V is final velocity, U is initial velocity. Okay, we're not going to do the examples. Very easy. You guys have already seen everything in E9. So skip. Oh, units conversion. We can do a little bit practice for this one. Okay, just a little bit practice. So, what is MPH? Anybody knows? Miles per hour. How do we do the units conversion? So let's look that step by step. Convert 632 miles per hour to meter per second. How do we do that? So first of all, we can write down 632 miles divided by 1 hour. That's literally what it means, right? And then we don't let miles. We need to convert miles into meters. So how much is 1 mile? 5,280 feet. But how much is 1 feet? This we can cancel out the mile. But how much is 1 feet? Well, 1 feet is, or 1 meter is 3.28 feet, right? So we can cancel out feet, and then we're left with meter. But this is not enough because hour is still here. So we want to know how much is 1 hour. We know that 1 hour is 3,600 seconds. And we want to put hours on the top so that it can cancel with the bottom hour in the front, right? So finally, we left with meter on the top, second on the bottom, and then we just need to do the numbers. So 632 times this divided by this and divided by that will give you the final value in meter per second, which is 280 meter per second. That's the general process to do it. When you times those things, just one more. When you times those and those and those, why does it work? Because this is basically 1, 1, 1, 1, right? 1 mile equal to this much feet. They are equivalent. 3.28 feet equal to 1 meter. 1 hour equal to 3,600 seconds, right? You're basically just times 1, 1, 1. So the final answer is the same as the initial one. Make sense? Okay. All right. Skip. Too easy. Okay, too easy. What's the difference between instantaneous velocity and average velocity? What is instantaneous velocity?
Velocity of that thing.
The velocity with only one displacement. What does with only one displacement means? You can say it in Chinese.
Displacement is it corresponds to one with
Nice try, but I'm not so sure what you're talking about.
Changing time is like limited to 0.
Okay, so instantaneous velocity is basically the velocity at that moment. How do we define velocity again? Velocity is the rate of change of displacement, so delta S over delta T, right? If we have, basically, you divided by delta T, that is an average velocity within this time period of this much, which basically, let's say, 100 meter of displacement over 10 seconds, that's the average velocity within that 10 seconds, right? But if you just want that single moment, which means 1 time stamp, that means the time, this delta t, should be as small as possible so that it's actually within 1 moment. Then what does 1 moment means? That means time is definitely infinitely small. Yeah, which is basically you're getting the limit of this when delta t is approaching to 0, right? You can think of instantaneous velocity as the average velocity of a very, very short time period. This time period is approaching very, very small, infinitely small, approaching to 0. How do you say 无穷小 in English? Infinitesimal, something like that? I forgot. But like small. Sorry. Okay, so that's a quick thing about instantaneous velocity. Basically, it's just an idea, same idea of average velocity, but with the delta t infinitely small. Okay. All right. So here, some details to look at. right? We call the limit as delta t approaches 0 in the equation this as the instantaneous velocity. Okay, instantaneous velocity. Okay. So let's move on. The Suva equation. Without looking at it, in DP level, in grade 11, I don't provide you data booklet in exam. And you're going to constantly need those equations. So a quick test, right? Thomas, say any one of the Suva equation. Anyone.
V equals U plus 18.
Very good. Alexander.
S equals UT plus 1/2 A times time squared.
Very good. Number 3. Look aside.
S equals to 1/2 U plus V times T.
Mm-hmm. No, last one. Hence, V squared. Very good. Okay. So that's our Suva equation. Make sure you remember all of them because you're going to constantly need them. And what's the condition to apply those Suva equation, Nancy? When can you apply the Suva equation? In free fall, sure. What kind of feature does free fall have? It has acceleration. So when you apply Suva equation, it needs to have acceleration. What else? Just acceleration?
Ignore air resistance.
Constant acceleration. So they can only be used if the acceleration A is a constant. Okay? Suva equation has a limitation. It can only be applied when acceleration is a constant. So if your forces changes constantly, which means your acceleration is going to change accordingly, can you apply Suva equation? No. Okay? No. So when you solve the problem, make sure you read the question carefully, see if it's constant acceleration. Constant acceleration. All right. Okay, so those are easy. Skip. 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 However, in MIP, I just asked you to remember the equation. In DP, I can walk you guys through of how to derive each one of them using velocity time graph for you to better remember it. So, if we use a velocity time graph, right? VT. We have 5 letters. S, U, V, A, T, where S is displacement, U is initial velocity, V is final velocity, A is acceleration, and T is time. Let's start from the very simple thing. If without acceleration, and what should the graph look like? Horizontal line, right? Straight horizontal line. Acceleration is 0, so the gradient is 0, so that's horizontal. Right? Okay. Now, let's say, what if it has acceleration? Can it still be horizontal? It should be a straight line, but has a slope, right? Like that. Right? Does it have initial velocity for my current case? Yes. Because when time equals to 0, velocity is not 0. So it has an initial velocity here. Right? The slope is acceleration, right? Okay. So, let's say this here is our final velocity v, and it takes this much time t to get there. We know that slope is acceleration. How do we calculate slope? Delta y over delta x. What is delta y here? V minus u, right? That's our delta y. V minus u. Make sense? What is our delta x? T. So you see, we finally get slope equal to a equal to v minus u over t. That means a equal to this. So if we times t from the both sides, we get at equal to v minus u. Rearrange it, we get v equals to u plus at. That's our first equation. First Christopher equation comes from the slope of the VT diagram. Okay? Okay, so that's the first one. Second one. We know the slope. What about area? What does the area under a VT graph represent? Displacement. Sure. So, let's say if we know initial velocity, if we know final velocity, and we know the time t, what is this shape of this area here? It's a trapezoid. And what's the area formula for trapezoid? Right. Area of a trapezoid equals to base plus top plus bottom times height, right? So what is top? Top is here, right? Which is u. What is bottom? V. What is height? T. So we rearrange it, we get u plus v over 2 times t. That's our second equation, right? How do you remember it? Basically just the formula for the area of trapezoid, right? That's our second equation. What about the third equation, s equal to ut plus 1 over 2 at squared? How do we get this one? Very good. How? How? Very, very good. If we split it into two sections, what's the area of this one here? ut. So ut, this part, actually represents this rectangular. What about this 1 over 2 at squared? How do we get this? Well, let's look at this one here, this triangle. What do we know about this triangle? Do we know this side? This side is t. What about this here? V minus u, right? V minus u. But we don't know anything about v and u, but we know a. So v minus u is basically delta v, right? Delta v equal to at. Very good. So this side, v minus u can be represented by at. So we know the base, we know the height. What's the formula for the area of triangle? Half base times height. So S 三角形 equal to half times base times height, which is base at, height is t, so 1 over 2 at squared. This is the area of this triangle. Clear? That's our third equation. And lastly, we have our final equation. How do we get the final equation? Now we already have three equations. Number one, v equal to u plus at. Number two, s equal to u plus v divided by 2 times t. Number 3, s equal to ut plus 1 over 2 at squared. What is our final equation? V squared equal to u squared plus 2as, right? So this one, we're going to need, it doesn't have time, right? So that means we need to substitute time. What can we do? Which one is easier to work with? This one and this one. Why not the last one? First of all, last one has 2 terms, and second of all, it has square, right? It will make everything more complicated. So let's just use the first 2 and supplement t, right? Let's say, use this one, let's work on t. T equals what?
V minus V minus V.
And then we just substitute this to here. We're going to get s equal to u plus v divided by 2 times v minus u over a, right? Okay, so nominator times nominator gives you a denominator times denominator gives you 2a, right? What do you call the thing on the top? 分子怎么说来着？
The numerator.
Numerator. Okay, so you have u plus v, which we can switch place, make it v plus u, right? You have a plus b times b, a minus b. What do you get? A squared minus b squared. So you have u, v plus u times v minus u, get v squared minus u squared. And then you times 2a from both sides. You're going to get 2as equal to v squared minus u squared. So finally you got v squared equal to u squared plus 2as. Is everything clear? Any questions? That's how you remember Suvat equation. It has logic within it. Beautifully logic. Okay. So skip. What is this? Okay, you can start from here. So everyone knows that when you drop an object, it picks up speed when it falls, right? It's gonna fall faster and faster. And Galileo did his famous free fall experiment on the Tower of Pisa long ago. Sorry, I'm hungry. And determined that all objects fall at the same acceleration in the absence of air resistance. Anybody knows about the story? Can anybody share with the rest of us if you know about the story? Yes?
About two animals with different paths from the top of the tower simultaneously.
Mm-hmm.
And the two balls seem to fall to the ground at the same time.
Okay, so the general story, as Raymond just mentioned, is Galileo released 2 size metal balls, one large, one small, at the same time. Okay, so here's Galileo. He released this ball and this ball, 2 metal balls at the same time. So time before Galileo, right? There is a famous scientist saying that the heavier an object is, the faster it will fall, right? Aristotle. And then Galileo did this with an example, and 2 metal balls reached the ground at the same time. At the same time. Okay? So, which is contradictory to this famous theory and revolutionized people's understanding about free fall, and we started to understand there is nothing to do with the mass in terms of free fall. 5 minutes break. Stop recording. All right, let's get continued. So about this experiment, that's it. And if you want to know more about it, there's tons of articles and videos about this stuff. You can search yourself on Google or YouTube. There's tons of resources, but we're not going to spend too much time on this one here. And if this is a vacuum, which means there's no air molecules inside it, right? Then there's no air resistance, right? The only force acting on the apple and the feather is just gravity, which means their motion is under free fall, right? Which the only force acting on them is gravity. And you will see that they're falling at the same rate, which means they're going to accelerate at the same rate, or their velocity is going to change in the same rate. So the acceleration is the same. Do I need to explain it? We have already went through those in NYP. So moving on. Pretty familiar with the free fall stuff. So okay, now we are pretty familiar with those. Skip. We just did the derivation with those formulas, so skip. We know that the slope of distance time graph is velocity from grade 9. We also know that slope of velocity time graph is acceleration from grade 9 as well. So we're not going to spend time on this. We also know that the area under the speed time graph is distance, or area under the speed time graph, velocity time graph is displacement. Okay. Now this here, we're going to start from here. So the goal is we need to qualitatively describe the effect of fluid resistance, which is including air resistance or water resistance, stuff like that, on falling objects or projectile, including reaching the terminal speed. Remember, in NYP, we always talk about free fall, which means we're going to ignore air resistance. But in DP, things could be a little bit more challenging. We need to discuss about what if we cannot ignore air resistance, right? What if the thing that we're throwing is a ping pong ball, not a metal ball? Then in this case, there's no way that you can ignore air resistance. So what do? At least we need to be able to qualitatively describing the motion with the presence of fluid resistance. So, what do we expect you to know? You should know what is meant by terminal speed or terminal velocity. Lucas, Qian, what is terminal velocity?
The max speed being under air resistance due to free fall.
What is the condition to reach the terminal speed? When
You accelerate under gravity, and the upward force of the air resistance of friction is equal to the downward force of gravity.
Very good. When the air resistance balance off the weight or gravity, then the net force of this falling object is going to be 0, because two forces balance out. Air resistance going up, gravity going down, cancels each other, no more acceleration, then the object will fall at a constant speed, which is the maximum speed that it can reach. Right? No more accelerating, no more acceleration. That is what we call the terminal speed. Right? This is when the drag force, which is the air resistance. Drag is another term for friction, for resistance. Exactly balance the weight. And so let's look at this. A blue whale suddenly materialized high above the ground. And the drag force D is proportional to the speed squared. So the faster it falls, the greater the drag force is, right? The greater the air resistance is. So thus, the whale picks up speed and the drag force also increases in the meantime. And once the drag force equals the whale's weight, the whale will stop accelerating and fall under its terminal velocity or terminal speed. So the key condition here is forces to balance out with each other. Okay, so relative velocity here just quickly went through. Let's look at this scenario. Consider two cars A and B. Okay. Suppose you're in car A. You're driving in a car A, which is moving in the positive direction of 20. And next to you is car B, is moving at positive 40. So from your own perspective, what's the velocity of car B? In which direction?
Then there's negative in the
Positive 20.
Positive 20, right? From your perspective, car B is moving with positive 20 meter per second, right? What's happening? What's happening is, let's say this is car A, which is you. This is car B, which is faster than you. Both of you moving forward, but this one is moving faster. So from your perspective, this car B, is moving forward with 20 meter per second, or positive 20 meter per second. Everything clear? Do you have questions? Good. But for car B's perspective, U is moving backwards with 20 meter per second. So if you're taking car B for perspective, for reference, then your velocity is negative 20 meter per second. Okay. So that's relative velocity. What about in 2 dimensions? What about that? Let's think about this. If you are in car A, which is moving at VA equal to positive 40, that means your velocity is this way. But car B is at right angle, moving at negative 20 as shown. So if it's negative 20, it should go in this direction, right? dV equal to 20. Then how are we going to do this? Any thoughts? Thomas, what do you think?
Maybe use trigonometry. I guess.
Okay.
So, the like forming a right triangle with
Okay.
40 and 20. So for the tangent. Yeah.
So are you saying doing a right triangle like that? This is 20, this is 40, and then find the resultant velocity like that?
Yeah.
Or in this case, 40 going this way, 20 going this way, so like that?
Yes.
Okay, no problem. Good guess. Let's see what is actually happening. If we're doing this like that. So, since A and B is moving perpendicular to one another, we're going to use a vector diagram to find velocity AB. And the solution, let's see. Draw the vector and use vector A and B, which is VA minus VB. So that being said, Thomas, you are on the right track, thinking using vector triangle, velocity triangle, but there's one tiny detail. Instead of adding them, we're finding relative velocity. Subtract, vector subtraction rather than vector addition. So if in this case, let's say VA is going this way, VB, if VB is going this way, instead of adding them like what we learned in MYP, which is just connect this one to this one, we're going to subtract them. How are we going to subtract? Well, isn't VA minus VB the same as VA plus negative VB? Right? The negative VB, isn't it just switch its direction 180 degree? So this is negative VB, this is VA, then that's it. That's the relative velocity of VAB. Alright? So, you're on the right track, just a tiny detail. Okay, very good. Very good. See? VB, then we just inverse it using negative VB, 180 degree. And then we use VA plus negative VB to get the relative velocity, the velocity of A relative to B. Okay, the velocity of A relative to B. Questions?
Mister, I don't really understand why subtraction.
Because you're taking B as a reference point. So if B is not moving, it makes sense that VA relative to, let's say, if B is the Earth, which means VB is not moving, right? We take Earth as our reference point. Then the velocity of A relative to Earth is the velocity of A itself. Does that make sense? Now, what if we don't take B as the Earth, but we take B as an object who is also moving, okay? Then in order to make sure that your reference point is based on another moving object, you have to balance out or trade off this object's own motion, right? By subtracting it from your own so that you can take that as a perspective. So understand why it's subtraction now? Okay, good. Smart. Alright. Okay, so how are you going to find the magnitude? Then you have a right triangle. You can use the math skills that you have to find the magnitude. Find the magnitude. Okay? Okay. Alright. Projectile motion. Finally. So this is something that you didn't learn in MIP. Why? Because in MIP, everything you learn is 1D motion. What does 1D stand for? One dimension, not direction. But well, it's close, but we would say it's one dimension. Now it's 2D, which means two dimension. Right? You have x-axis and y-axis. It's moving in both x-axis and y-axis. We learn free fall because free fall is only happening in vertical direction. That's 1D. But now with projectile motion, it's 2D. Right? So a projectile is an object that has been given an initial velocity by some sort of short-lived force, and then moves through the air under the influence of gravity. Such as baseball, stones, bullets are all examples of projectile executing projectile motion. And like that. Right? Like that. And you know all the objects moving through the air feel a resistance, right? So, but for projectile motion, we will also ignore the air resistance for now. Okay, so how are we going to analyze projectile motion? Regardless of the air resistance, the vertical and the horizontal components of the velocity of an object in projectile motion are independent. What does that mean? So whatever that happens in the vertical direction has no influence in your horizontal direction. Whatever that happens in your horizontal direction has no influence on your vertical direction. Right? That being said, So, let's say this is a table where we have a ball, right? And this ball initially at rest. Now, if we give it a sudden push so that it has an initial velocity, we know that it will, because it's still on the table, so it will move in this direction. Once it left the table, it will start to jump, right? So we kind of expect that it will move horizontally and at the same time falling downward, right? So we can kind of think of it like its trajectory is kind of like this, right? So let me give you a small example with a tennis ball here or a golf ball, whatever works the best. Now, right now I have this ball. If I give it a sudden push, let's say, right? It looks like that. 哎呀，一会儿再说。So, what you can see is it kind of goes like that, right? Kind of like goes like that. So, what is actually happening? Let's start analyzing. If we ignore the air resistance, what are the forces at this position?
Gravitational force.
Any other forces?
Initial force.
If we ignore air resistance,
No.
only this force, right? But it has an initial velocity in x-axis, right? Is there any forces in horizontally? If no forces in horizontal direction, is there going to be acceleration in horizontal direction? If there's no acceleration, that means no acceleration to speed up this horizontal initial velocity, and no acceleration to slow down the horizontal velocity. Then what happened to this ux? It just stays ux, right? It just stays as it is, which means in x-axis, what type of motion it is doing?
Constant velocity.
It's moving under constant velocity in x-axis, right? So we call that uniform linear motion in x-axis. Okay, that's x-axis. What about y-axis? We know that they're independent from each other. Initially, does it have Vy? Initially? No, because it's not moving, right? So initially Vy is 0. But after it left the table, does it have acceleration?
Yes.
Is acceleration a constant?
Yes.
Can you apply to what?
Yes.
So x-axis, vertically, it's free fall. Right? So to sum up, x direction, y direction. That is projectile motion. That is projectile motion. Okay, I'm going to do a live experiment here with a projectile launcher, and let's see how that works. Okay, I will stop sharing on this here, and then I will start sharing with my computer, my laptop in the back. And you guys can see what's happening here in my screen. I will share it, so don't you worry. I will share it. Right now here, as you can see on this big screen, is a LoggerPro, okay? LoggerPro software on my laptop. And currently, my laptop is connected with the LabQuest 2, which is a device that helps me to collect data. And this, you guys can come back and see the setup here, which I don't have a table in the front, so I cannot do that there. So here I have this, what we call a projectile launcher, okay? It can launch the projectile. How does it work? So we have this, a metal ball here, and we can put it into this projectile launcher. I have a pump where I can pump air inside so that it will use the pressed air to push the projectile outwards. We can adjust the angles here. Right now I want it to be, let's say 30 degrees, so put it here, okay? And I wanted to see, store last round. I wanted to be able to see how fast this projectile is being launched. So what do? I pump into air, and then 1, 2, 3. So what is the initial speed that's being pumped up? 2.952 meters per second. So if we know this value here, and we know that the angle is 30 degrees, let's do a quick calculation here. So if we draw the experiment setup, we know that this here is the launcher, right? The launcher has an angle of 30 degrees with the horizontal, right? So the ball is actually being shooting in this direction, so the trajectory looks like that, right? And we know that the initial velocity is 2.952. That's actually very accurate or precise to the thousandth place. So we know that this initial velocity equals to 2.952 meters per second. After knowing that for projectile motion, the horizontal and the vertical speed or motion is independent from each other, what can we do?
Split it into vertical and horizontal.
Split it into vertical component and horizontal component. How can we split this velocity here? How? Do you still remember how to add vectors? If we have two vectors connected head to tail, then the resultant vector is just from here pointing to here, right? Similarly, now we have this one. How can we decompose it? We can use two vectors, which is horizontal and vertical, as long as they're connected head to tail. So we can decompose it using this two velocity vector here. Which means, let's use u, which is initial velocity to represent it. Which means we can use ux, which is the initial velocity of x-axis, and uy, which is the initial velocity of the y-axis to represent it, right? And we know that this triangle here has an angle of 30 degrees, and this is a right triangle. And we know that in this velocity triangle, vector triangle, that the hypotenuse is how long?
2.95.
Hypotenuse is 2.952, and we know this angle is 30 degrees. What about this one here?
Cosine 30 times 2.
Cosine 30, this one here?
Sine.
So it's sine 30 degree times hypotenuse, which is 2.952. Sine 30 degree is 1/2, right? So you just need to divide by 2, which you're gonna get. Let's, for the sake of easiness, just use 3.
Yeah.
Okay? Then we know that this vertical initial velocity is gonna equal to 1.5. What about this initial velocity here? Cosine 30 degree times 3, that's gonna give you how much? Yeah, but like in decimal place.
4.24.
Hmm?
4.24.
How's that possible? Your hypotenuse is only 3, and then you get 4 point something?
2.5,
That's it.
2.60.
2.5,
2.598, so
2.59, let's just say 2.6. For the sake of simplicity, okay?
Yeah.
When you're dealing with your data, you need to use 2.952. Okay, here is just a demo for simplicity, okay, showing you the methodology. So, what do we know about x direction?
2.6
Constant. And what do we know about y-axis?
1.5.
It's the initial velocity.
Okay, so let's list out what do we know. For now, we know that uy equals positive 1.5 because it's going up meter per second. We know ux. I wanted to separate those two because this is y direction, which is free fall. This is x direction, which is uniform motion. Okay, and let me remove those unrelated information. So, what if I wanted to find out before it reached the ground, before this projectile reached the ground, how far horizontally it has been traveled, and what's the maximum height it can reach? How can we do that?
Suvat y.
Okay, so about to find out height.
Yes.
Alright, so what do we know in y action? We already know the initial velocity. Do we know final velocity?
0.
Yes.
If we wanted to find out the height, then the final velocity, final position is here, right? So what's the final velocity in y direction? It must be 0 in order to reach the maximum height. Because if it's not, it was still going up. So Vy equal to 0. What else do we know?
Or is on.
No.
Acceleration.
Focus on,
Acceleration is
right? We know 3. Can we figure out h? Which is about to use in this case?
V squared
Equals to U squared.
Right. V squared equals to u squared plus 2as. S is h, right? So we can solve for h. H equals v squared minus u squared over 2a. V is 0. U is 1.5 squared. A is
9.81. Negative 9.81.
Why? Why negative? Because I set this as
Upward.
positive, initially going up. So your acceleration needs to be negative. So that you can find out how high up. 1.5 squared divided by 2 times negative, 2 times 9.81.
Zero point zero
0.07.
8.
8 meter. That's the maximum height that the projectile just reached. Can we calculate the time needed for matching the maximum height here? Okay. How?
V equals U plus.
Okay. So let me roll down what we have already known here. S U V A T. We already know solve the S, which is 0.78 meter. U is plus 1.5. V is 0. A is negative 9.81. T, we're looking for T. What equation can we solve for T? So T, can we use delta V over A, which is 0 minus 1.5 over negative this. We're going to get, for the sake of simplicity, so we're going to get 0.015
Yeah.
seconds, right?
But yeah,
So can you figure out how far away horizontally have traveled?
yeah.
How?
Yeah.
Okay, so which is
Yeah, the times
2.6 times 2.6 times 0.015. Is that correct?
times
Is that correct?
times two.
Y times 2.
Because you have to go
Goes
back
up and down.
What is this time that you solved?
in the middle.
The time you solved is half of the range when it reaches the maximum height. It takes the same amount of time to drop from the maximum height to the original level. So this T is 0.015. It takes this much time to travel here, and it takes another 0.015 to travel here. So the range, which is the horizontal distance that it traveled, is equal to Ux times 2 times T here. Does that make sense? Any questions? We're good? Very good. Okay. So, as you can tell, we have LoggerPro, we have LabQuest 2, we have Projectile Launcher, and those devices can give you very accurate and precise values, which is good for your IA. And you can collect very good data from it. Okay? That's the demo for the projectile motion. So I'm gonna stop sharing in the back, and let's back to the lecture. Okay, with the okay. All right, let's come back to here. So, how do we analyze projectile motion? We can use a grid like that to help us understand what exactly is going on. So when we throw a ball, in the example of Mr. Kai just launched that projectile, you see, it's that the trajectory looks like that. So if we took pictures of same time interval, okay, X is the same time interval, we will find out the trajectory like that. And it's actually a parabolic line. How do you pronounce it? Parabola?
Yes.
Parabola? Okay, parabola. And you see, this is the horizontal motion. Every time it moves the same distance, right? It moves forward in the same distance. But vertically, at very initial, it goes up very fast, but it will slow down, right, by the gravity. So each time it gets smaller, shorter and shorter, the distance, closer and closer. When it reaches the maximum height, it starts to fall, and each time it falls further and further because it's speeding up. But horizontally it's still moving in the same distance each time. Same amount of distance each time. Does that make sense? Questions? We're good? Okay. Why is AX equal to 0?
Because the last one because
What causes acceleration?
Change
Changing speed is the result from acceleration, not the cause of acceleration. Force. So what is ax equal to 0? Because there's no force that pushing it forward or slowing down, right? There's no force in the horizontal way. Why is it slowed down first and then speed up later in vertical direction? Gravity. Because we have force, the weight acting on the projectile. Does that make sense? Okay. Alright, parabolic. Okay, the trajectory is parabolic without the presence of air, with the absence of the air. So, what if there's air resistance? Without air resistance, it's a perfect ideal parabolic. But what if there is air resistance? There's acceleration in the x direction, right? So we know that in y direction, acceleration is going to be this way. What about x direction? It's going to be in the opposite direction of the motion, right? Okay, which means in horizontal direction, it's no longer uniform linear motion. It will gradually slow down, right? So would it still be able to reach this far? Can it be here? Not even possible because it's been slowing down. So it has to be somewhere here, right? So the possible shape could be looking at. Can it still reach the same height though? Why?
Because height is still
Wait, no, because there's also air resistance.
Exactly. When you're going up, there's still air resistance because air resistance is in the opposite motion. So air resistance is actually when you draw it. At this position, air resistance is here. At this position, air resistance is here. Here, 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 here. That is the air resistance. Does that make sense? Because air resistance is always in the opposite direction of the motion. So can you reach the maximum height? No. It cannot reach the same maximum height. So maybe here and here, then you're going to have this trajectory kind of like that. Does that make sense? Questions? See? You're not going to reach the maximum height, and you're not going to reach the maximum range. Okay? All right. Peak is to the left, lower of the original one. Okay. Oh, by the way, if ignore air resistance, parabolic is symmetric, right? Symmetrical. But with the air resistance, is this still symmetrical? No. Okay, that's it for today's class. Stop recording.